Hey, it's unit 4. We're talking about polynomials, and that's pretty cool. So I really like this unit, but for the first video here, we're going to do, there's my dog yawning. We're going to do sort of like an overview. So here's something I keyed up already, because I don't know, it's all definitions and stuff and ideas. And so we'll talk about the ideas, but I've already done most of the writing on this. So we'll see how it goes, and I'll upload this overall key document once I'm done with everything. By and large, that'll include kind of like an answer key. So I probably won't go through all the problems in these videos. I'll just talk about them in general, and then you'll be able to find the answer key. So in our polynomials unit, we're going to talk about polynomials as functions, so something like that on a graph. We're also going to be talking about, well, how can I solve a polynomial like this? And what does that even mean, solve? A lot of different ideas we can do. So we're kind of dealing with the equations, or like how do we deal with breaking them down algebraically, mathematically, and how do we deal with them as functions? So moving into our first idea to start, what is a polynomial? And it's a collection of terms where all of our degrees are natural, or better yet, we could say, or whole numbers. And by that we mean, if I've got x to the power of n has to be a natural number, or we could have like x to the power of 0 as well. And I'm going to have to go kill my dog. 1 second. Anyway, so I got that squeak toy. So we're allowed to have whole numbers because x to the power of 0 is just 1. But then again, that's kind of like, okay, not that exciting. By and large, you can kind of talk about how if we've got a polynomial, it's going to have functions or expressions, terms where our degrees are all natural numbers, so positive integers. We already also know some of these other ideas, or at least we should. So the degree of the polynomial is the highest degree on a term. And so if I've got something like the example we did above, whatever was x cubed plus x squared or whatever, blah, 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 our leading term often, but whatever our highest degree is the degree of our overall polynomial. So this would be a third degree polynomial because it's got the highest degree of 3. Beyond that, one of the key ideas here with the degree of a polynomial is that if you have a degree of a polynomial, that degree is important because it kind of determines what our function is going to look like. So if you think about this in terms of graphing, understanding what the degree of a polynomial is kind of the whole point of what a graph is going to look like, or how is our polynomial going to act, what is making this polynomial. All that's based on our degree, and so that's kind of a big deal. Another thing that's really helpful for us to understand is this idea of end behavior. So we've got like a positive and a negative end. So our negative end is what's closer to the negative side of x, and positive is on the positive side of x. And this is sort of the direction which our ends are facing. So if I've got this, we could say that our behavior is it starts at our negative end in quadrant 3 over here, and then it continues over to quadrant 1. And so that's kind of an idea for end behavior. And we've got a couple options for how this can work. You can have something that's like this, where it goes from 3 to 1, or you could go from 2 to 4 with something like this. And then we'll do one in orange, where we've got 2 to 1, if we got something like that. Or we could do, I don't know, purple. Yellow never shows up well. We could also do something like that, where it's 3 to 4. So there's a number of different ways that we could see end behavior. And that end behavior is kind of determined by, you got it, the degree of the polynomial, in addition to one other thing, but we'll talk about that. As far as domain and range goes, if we have, where's my button? There we go. If I've got a polynomial function, essentially x can be anything. So we're always going to have this x being an element of the real. Anything is allowed to go into our polynomial functions. The range, I didn't fill this one in because it's kind of a bigger idea. So let's talk about that out loud. The range of a function depends on the function. So we can say depends. But for a polynomial, we're going to have sort of two options. Option 1 is if we have an odd degree, and we're going to talk more about odd versus, you guessed it, even degree with an E beforehand, so odd and even degree. With an odd degree, our range is always going to be able to be everything. And the reason for that is that if you have an odd degree, it's always going to have end behavior that's going like this. Starts at one corner, ends in the exact opposite. It could end up doing, you know, like this instead, where it starts by being positive and then ends negative. But it always has this general trend to start on opposite corners. And so for that reason, it's always going to include everything. An even degree polynomial, unfortunately, is a little more complicated. And for this, it depends on what the graph looks like. But an even degree polynomial is always going to follow this pattern where it's something like that. Boom, boom. Yes, Scout, I know, but or like this, where instead of being on opposite corners, it's on like corresponding corners. They're both pointing down or both pointing up. And so this is going to be depends on max or min. So our range will depend on the max or the min. And that's just like when we were dealing with quadratics. With a quadratic, we've got this one point, our vertex, and this is our like overall maximum. So if this is a maximum, then everything below that is cool, but nothing above it is cool. And so that defines our range. Intercepts, lots we can say here. The points at which the polynomial intersects with an axis. Particularly, we care about our x-intercepts the most. So let's say if this is our function. On this, I do have a y-intercept in here, which is nice, but whatever. There's always going to be just one y-intercept. And we have x-intercepts based on the degree of our polynomial, where our amount of x-intercepts is equal to the degree of the polynomial. So up to n, up to, here we go, n x-intercepts, where that's the worst where ever. Wow. Nice writing, Mr. Herman, where n is the degree of the polynomial. And when I say up to, it's not always going to be equal to that, right? So this is a degree 3 polynomial, and there happens to be 1, 2, 3 intercepts, but it could be different. And we'll look at that in a minute here. Another thing that we can add to this that's really important that I'll add into the key as I go along is that if I have these intercepts, they're based on the roots and factors of the function. Now, what this means is that if I've got something like x squared minus 4, we know our intercepts are based on the x squared minus 4 is equal to x plus 2, x minus 2. And so these are our two roots, -2 and +2. So for a cubic function, these zeros are still based on the factors, based on the roots of our equation. Even versus odd, when we're talking about this, we're going to break an idea up here. When I say even or odd in like calculus sense, I mean very specifically that it has an exactly opposite, right? So if I've got a function like this, we'll say this is perfectly odd. Here's our axis. I totally missed that. Let's try that again. There's our axis. This does the exact opposite thing on either side. So this would be odd. Okay, and it's kind of like symmetrical in that it's exactly opposite. So if I looked at this point here, it's the exact opposite of the corresponding x over there. And if I looked at the area under this curve, it's exactly the opposite as this. And so if I was like adding those areas, it would cancel out. An even function is one where it's exactly the same on either side. And so over here is going to be exactly the same y value. Our area under this side is going to be exactly the same area under this side. And so when we talk about odd or even functions, we generally talk about ones that are perfectly odd or perfectly even. In terms of polynomials, when I say an odd polynomial, I mean a polynomial with a degree that is odd. Okay, that's great. That's handy. With even polynomials, it's just a degree that's even. And what I recommend you to do is go to page 113 to see more characteristics of even and odd polynomial functions. But we're going to run into a lot of them, and I think it's going to make some sense as we go through. So let's take a look at a number of different functions here. Let's start at degree 0. So degree 0 is something like y equals 5, this constant value of 5. We could kind of include this imaginary x to the power of 0 behind it because, well, that's just going to be there. And some of the characteristics of this, it creates a flat horizontal line. Yeah, good, we know that. And it's going to have a y-intercept, right? But it's going to have no x-intercepts unless it's on our x-axis, in which case it's going to have infinite x-intercepts. And that kind of makes sense, right? If it's on the axis, it's going to be constantly touching the axis. It's like intercept central. But if it's not on the x-axis, it's parallel to the x-axis, so they'll never touch. Okay, if we've got a degree 1, here's an example, y equals x minus 6. So there's a vague graph of that. We've kind of got this general form we've already worked with, y equals mx plus b. And so using this, we always knew there was one y-intercept at whatever our constant value was. Usually we use the letter b. And there's also an x-intercept. There's always one x-intercept. So there's one x-intercept, always. And that's probably sufficient for our needs right now. Here's another one. I've got y equals x squared minus 4, and then I just started scribbling more or less. For x squared minus 4, we know we have the one y-intercept, and that's equal to our constant value. So if we think about this in terms of like y equals ax squared plus bx plus c, then our y-intercept is just a constant, and our a value is kind of a big deal in determining which way our graph is going to go. Okay, and so if we've got a function like this where our a value is positive, so if a is greater than 0, it's positive, then our graph is going to have a minimum. Okay, and its end behavior is it's going to start in 2 and it's going to go to 1. If a is negative, it's going to have a max and it's going to go from 3 to 4. One thing to consider while I'm going over these is if I drew a graph like this, notice that obviously this is in quadrant 2 and this is in quadrant 2. You have to think for our end, it's going to extrapolate. So it's eventually going to end up in quadrant 1. So that would have an end behavior like that. The last thing we can talk about on this graph are intercepts. For our x-intercepts, we can have 0 if we wanted to, where we have something like this. We could have 1 if we had something like this. Or we can have 2. And so like we said, the degree of this, wow, I missed that underline. The degree of this tells us the maximum amount of x-intercepts. But with an even function, we can have 1 or we can have none in this case. So what about when we've got degree 3? Well, with the degree 3 term, we'll use this kind of A, B, C notation. We'll just say our A is our leading coefficient. So if our leading coefficient A is positive, then we're going to still have an infinite range, right? So there's no maximum or minimum. But importantly, our end behavior is going to go from 3 to 1. Whereas if A is negative, then it's going to go from 2 to 4. Cool, so that would be something like this, right? Very sloppy, I know, but it curves, trust me. So here's my graph. On this, my maximum number of intercepts is 3, right? So I've got 1, 2, 3. So for intercepts, I could have 3, but I could also have something like this where it crosses over, but then it just touches and then goes, right? With these curves, this is still a cubic, so it could have 2. And the minimum I could have is something like this, where it goes like that. And so I could have 1. But there's always going to be at least 1. For an odd function, it has to start in one corner and go to the opposite side. So we know it has to cross the x-axis at some point. All right, degree 4 and degree 5. For these ones, nothing super surprising. With this, our rules here are exactly the same, so just copy paste those. And you can have 0 still for our possible x-intercepts, all the way to 4 possible intercepts, like this one here. Same idea, again, our rules, copy them down, right? They're applying the same way, but we can have between 1 and 5 x-intercepts for a quintic function, a degree 5 function. And this pattern kind of continues, and that should make sense if you go back up and you talk about our kind of characteristics on page 113. That whole thing it's just full of ideas which you copy down. Okay, foundational. Very foundational stuff, and so make sure you've got a decent idea on what all these pieces mean. But tomorrow, and by tomorrow I mean next lesson, I don't know, I'm teaching it tomorrow, I don't know when I'm going to make the video. Next lesson we're going to do something a little more mathy, so get ready for that. And in the meantime, I hope this video was helpful. I'll see you in the next one.